Hello. So in the previous lecture, we understand about the how this unit third mining data streams has come to an existence with the with our book, this book, this second book, Anand Rajman and Jeffrey Duellman. How this book no, has contributed in our data three, data four. So we understand what is the way and flow of that part. Let's move. What next we need to understand? Okay. So we need to understand what really the mining data streams is all about. So for that, we need to go for the frequent item sets because as it is, we need to understand about the this stream concept this time. So let's go to the stream concept that is you know unit four of this book. Let's go for let's go to book. Yeah. Okay. This is the what we are focusing on. Need to focus right now. Mining data stream, that is unit 3, this one. This is taken by this textbook and reference book. Okay. Let's start. So whatever is defined in this book is defined for the data mining, how to mine those data. And in the previous units we also came across about how it is different for machine learning and how data mining and machine learning is different. Here we will focus how we will do our operations on the stream data, how we will do operations on our stream data. Okay. So how it will do the operations on the stream data. Data arrives in a stream or streams, and if it is not processed immediately or stored, then it is lost forever. Moreover, we shall assume that the data arrives so rapidly that it is not feasible to store it all in active storage. Okay. That is in a conventional database because it's just streaming. It's lost its value in between, and then interact with at the time of the choosing. Okay. So the algorithms are very much different for processing the stream thing, which is written here, which is written here. So we summarize. So how are we going to understand the things? Let have an approach. Let learn an approach, which is let's summarize a stream is to look at only a fixed length window. How we will approach? We will summarize a stream to look only a fixed length window. That is the window concept of it belongs to networking. Consists of the last n elements for some typical large n. We then query the window as if it is where a relation in a database. Okay. If there are many streams or n is large, we may not be able to store the entire window for every stream. So we need to summarize even the windows. We address the fundamental problem of maintaining approximate count on the numbers of ones in the window of the bit stream while using much less space than would be needed to store entire window itself. This technique generally works on the approximation, and use various time distance. For understanding this, how this window technique works, we have derived a model which is known as the stream data model. Okay, how it works? It works like this. we have a data stream management system here, and many streams are entering. Okay, 1527400 QWERT, all this and these numbers. There we have a stream processor. This processes the thing with limited time in storage, and we have archival to storage. We have archival to storage, and from this from in this stream standing queries, we can go for that or queries to get the things done. So what is this is what data stream management system, and what we can say that the stream model, which is was to derive a data stream management system. Data, data stream data model is mainly not a way to process through the data stream management system. So in a database management system in past, we view a stream processor as kind of data management system, the high level organization of which we have suggested in a figure 4.1. This is figure that many streams are coming and the stream processors are working, from which it is interacting with the archival storage as well as the limited work storage, and also the stream is there after ad hoc queries. So any number of stream can enter the stream. Each stream can provide elements or of its own schedule. They do not have the same data or data rates, and time between the elements of one stream need not to be involved. These streams need not to be informed. Uniform as a time, and it's maybe come in 1 second interval, maybe it comes to the 5 second interval. The fact that the rate of the arrival of the stream elements is not under the control of the system distinguishes stream processing from the processing of a data as goes on within a database management system. The latter system controls the rate or which data is read from the disk. Therefore, never has a worry about the data getting lost as it attempts to execute queries. Streams may be archived in large archival store, but we assume it is not possible to answer queries for the archival store. Can be only examined under special circumstances using time-consuming retrieval process. There is also a working store for this, in which we summarize or part of streams may be placed, which can be answered queries as per need. The working in this management system, the working store might be a disk or main memory, depending on how fast we need to process the queries. But either way, we define our capacity that we can't store all the stream data. That's that's our analogy. So we understand here that we can't store this data on the main memory or the secondary memory of the single system. We need a parallelism. It need a cloud computing support. This is data streaming system, and the processing systems need a window management support, and from which our ad hoc queries will interact with the archival storage as well as the limited working storage. You can say that the RAM, and then as per need they give it out as a output stream. That's what our stream data model is all about. Let's move ahead. What is the example of the stream data sources? There are many examples. Let us consider some of the ways in which the stream rise naturally. First example is the sensor data. What is really the sensor data is all about? Imagine a temperature sensor bobbing about the ocean. I have give this example in a class. Sending back to a base station reading to the surface temperature each hour. The data processed by the sensor is a stream of real numbers. It is not very interesting stream since the data rate is low. It would not stress modern technology, and the entire stream would be kept in the main memory, especially forever. Now, if the sensor is a GPS unit, let us report surface height instead of a temperature. So the surface height varies quite rapidly compared to the temperature. So might we have a sensor sent back a reading every 10th of the second? Every second, a 4-byte real number needs to produce 3.5 megabyte per day. Understand this, and which is which is very much tough for any SQL disk or a main memory to gather this data. What is the gist of this? We need to understand the temperature of the surface of the ocean. Okay, and we need to which is which we taken as a stream. You know, we just put on sensors, and as per our technology, we are getting the data done. Okay, we're getting the stream done. We're getting the stream done. Okay, and how it is done? It is done through when the sensor sends a 4 byte real number each time, and due to the surface of the ocean is so big, we get a 3.5 megabyte per day, which is impossible for any single system to perform. So one system might, if we need to understand, if we put a one sensor, it's very easy to handle, but if you put the sensor across the ocean, it is very tough to handle. To learn something about ocean behavior, okay. So if you want to learn something about ocean behavior, we need to put a million sensors. So each sending a stream, at the rate of the 10%. The million sensors is not very many. There would be 150 square miles of this cone, square kilometers of ocean near boundary. So this 3.5 terabyte data, which is running every day, we definitely need not to think about what can happen, what in storage, and what can only be achieved. So we need to understand this very carefully. This is how the stream data stream data processing is need to be taken care, because such a high the data is coming such a high volume, and upon in the various velocity that one should think which mechanism we should process the data. Now the second example is of the image data, which is what we getting from the satellites. Okay, satellites often sends data and stream data in the form of terabytes images per day. Okay, surveillance cameras produce images with lower resolution than satellite, but there can be many of them. Each produce stream of images at interval like 1 second. London is said to have 6 million such as camera each producing streams. So, we can't get a clear picture of the 3D by a single 2D camera. We just put more camera and just overlap those pictures. So, these pictures also need a processing unit. This time we get a real image. So, that's what I'm saying, how the things govern this stream world. We have also an example of the internet and the web traffic. Switching more node in the middle of the internet receives stream of packets, 5 packets, from many inputs routes them to the outputs. Normally, the job of the switch is to transmit, not to retain it for a query. But there is a tendency to more capability to switch, and the ability to detect denial of service attacks, or the ability to reroute packets based on the information about condition in the network. The site receives streams of various types. What is this particular part is saying that we have a network, and in the network we have a switch. Switch is basically used for the just switching the data from one place to another. But we think to put more abilities in that. We try to put try to put some functional methodology which help us switch to the detect the denial of service attack, and they have an ability when these things are detected, then they will able to do the packet based on the information. The information to the user that the condition of the network which is true, which is very much helpful for the future. Okay. So websites also receives streams, like Google have a very much receives several hundred billion searches queries per day. Yahoo accept billions, million billions per day. Various many interesting things can be learned from these streams. For example, an increase in queries like so thought enable us to track the speed of virus. Such an increase in the click rate of the link could indicate some news connect to the page. But when a link is broken and streams need to repair. Now we are always putting the things like the stream queries, the figure 4.1 also. We have our stream queries, standing queries, stream queries. What really the stream queries is all about? What is the stream queries are there? There are two ways that queries can ask about stream. We show in 4.1 place within the processor where standing queries are stored. These queries are in a sense permanently executing and produce product output at appropriate times. Okay. So what is the thing is that we have when we query, they usually keep it in their database and permanently executing that query without our interest. But whenever anybody needs that query, they answer that query. Example, if I just give a query of for nowadays COVID is there. Put I am so thought what is the way COVID sector or not. Many of you have also asked these questions on the Google, Yahoo, Bing, many like searching sites. So they just put on the query they have, recent queries. You're trying to search, mine, search the query, what is the most frequent queries of the day or the line or the week, and then they push to get result to us. Okay. So this is how stream queries works. Okay. Now for that we are again taking some example. Like the stream produced by the ocean surface temperature sensor mentioned in the paper might have a standing query to output an alert whenever the temperature exceeds 25 degrees centigrade. These queries are easily answered since depend only on the most recent stream value. Okay. Alternatively, you might have a standing query that each time a new reading arises produces the average of the 24 most recent readings. Because these readings are always in the database. But query also can be answered easily stored at the most recent stream elements. When new stream element arises, you can draw from the working store. The most recent and it will never again be needed unless there is some other standing query that is answered. Now, the query you might ask is the maximum temperature ever recorded by the sensors. So these are the things we have in our simple as a simple summary. We can get from the query results. Okay. So whenever the new queries arise, we try to put in our database and fix them. Anybody asks, then this historical queries will help us to get our data things done. Let the things done. Okay. So we understand how queries is done in the system, how those queries can be the queries are recorded in the database, and it is new queries there, they add it, and if other if around the globe anybody asks similar queries, they used to give the answer. So they're performing the ad hoc queries for really make the system up to date. So the other form of the query is ad hoc. A question asks about is once about the current state of the stream or streams. If we do not store all streams entirely, normally we cannot, then we cannot expect to answer arbitrary queries about the streams. If we have some idea of what kind of queries will be asked to that query interface, then we can prepare for them for storing appropriate parts of the summaries of summaries of the streams. What really we do is really in the practical. So for that we have understand that we use the sliding window concept. So if you want a facility to ask a wide variety of ad hoc queries, the common approach is to is a sliding window of each stream in the working store. Sliding window can be the most recent and elements of the stream. For some element, it can be all elements that arrive within the last t times. Example, most recent we can say that in 1 day period, how much elements we are getting, how many elements we are getting. So in this regard, we take the stream top element as a tuple, and we can treat window as a relation query, and which can so we can implement our SQL query.
So of course the stream management system must keep the window fresh and deleting the old elements as the new ones to come in. So this is the way how the sliding window things done, and this is one of the most important thing to understand what really it is. You know, if one day if we a sliding window can be most recent and elements of the stream, and or it can be elements that arrive within the last t units. For example, one day. If we regard each stream elements as a tuple, we can treat the window as a relation and query it as a SQL query. Of course, the stream management system must keep the window fresh and deleting the old elements as continuous. Okay, that's right. So let's have an example to really understand this. Let's have we have a website often like to report the number of the unique users over the past month. You know, if we take the each login as a stream element, we can maintain the window that is all logins in the most recent month. We must associate the arrival time with each login so we know when it no longer belongs to the window. We think window as a relation of the logins, name, comma, time. Then it is simple to get the number of unique users over the past month. How it is done, let's again and relate with this. A sliding window can be the most recent n elements of the stream. And most recent elements we need, and here we are getting a question from the past one. So most recent thing. So we need to maintain all login of the month of the past month, and then we will associate the arrival time with each login. Now, what is the really sliding window is? We get the most recent element. This is where it is the past month, and for some and the sliding window, it can all be elements just arrive within the last t time units. So last t time units is here it is. So is a recent met and how we are getting that ad hoc query. So we here we try to form a relation, you know. So here the relation is the logins. Logins relation is the name and time. So which stream has arrived at this time, and then we create a query for getting the things done. Like here we are selecting account, which is the distinct element, distinct name, and from login, and we define t is there. The font t must be greater than equal to constant present time of 1 month before the current time. So what is the thing is we're trying to implement this definition within the coming example. The sliding window can be the most recent and element of a string. An element is 1 month. For n, for 1 month, it can all be element that arrive within the t time units. So we just derive some time period. So within the t time unit, whatever streams will come, we will try to make a relation with that. With regard to stream element, we take it as a tuple and window as a relation query. We try to maintain a stream we try to define a relation, and after that we define a SQL query. So what we are doing that again, we are focusing on thing that we are focusing the thing like for each query we are logging the thing again, and we are taking the end time as a month, and we creating a relation login, and which is always and we creating a time that is 1 month, and where we are creating a time of 1 month. So we create this query as per our information, and where t is a constant that represents the time 1 month before the current time. Okay. Whenever this query will run, you always get the stream data query with the relationship login for the last 1 month. So we are able to maintain the entire stream login for the past one in working storage. For this, we need a 1 month data actually. However, for the larger sites, that data is not up to terabyte, so surely we can store database. So this is how we try to get a we get our analytics from a stream data model with the help of a sliding data. Okay. So we understand that this is a complex phenomenon, but really the issues in the stream process. Okay. Before let's have an understanding what really the core steps. The first course is introduction to stream concept, stream data model, and architecture. Okay. And what we have learned right now, and then we focusing towards stream computing, which we are learning about the Windows. Right now, we will focus, next we'll focus about sampling in the sample, how the sampling is done. Before that, let's understand this thing, how the issues of this stream, what are the issues in stream processing. Before proceed to this algorithm, let us consider the constraints under which we work when dealing with the streams. First, streams often deliver element very rapidly. We must process elements in real time or we lose the opportunity to process them all without accessing the archival storage. Okay. First, it often important than most stream processing algorithm is rooted in main memory. Main memory is RAM, which access secondary storage or which rare access to secondary storage. Moreover, when streams are slow, as in sensor data example, there may be many such streams. When you stream by itself, any process in a small amount of main memory. The requirement of those together can easily exceed the amount of the available main memory. Thus, many problems about streams data would be easy to solve if it has enough memory, but become rather hard and require the invention of the new techniques in order to execute them at a realistic rate of the machine of the realistic specs. Now we're too generalized about stream algorithm. Then often it is more efficient to get approximate answer to a problem than an exact solution. In the stream management system, from the stream management system, we get the approximate answer. With the help of the last month data, in the previous example, we get an approximate answer. Chapter, in the chapter 3, we learn about our techniques of the randomness of the behavior. So we can also use these techniques here also in the stream data to standard. Now the thing is how the sampling is done in the data stream, which is really the next part of our subject. How the sampling is done, and this we will learn in our next video.